So, hello everyone, and thanks for the introduction. In this talk, I'll give you some insights about Christopher and my work, which is about how physical characteristics can be used to determine the sender of a received message and how this information can be used to detect intrusions. I think all of you have heard that cars are getting more and more equipped with additional functionality, which requires some kind of wireless connections. For example, cloud services to provide real-time traffic information, or Bluetooth to connect your smartphone and so on. But these interfaces do not only provide comfort functions, but also offers potential attackers to access your car without prior physical access. And that this is not just a theoretical risk. It was demonstrated by Miller and Walasek some years ago. The researchers have shown that they were able to compromise an ECU, which is for electronic control unit. And from this ECU, they were able to control several functionalities in the car, like the engine, brakes, and also the steering. And this led to a recall of 1.4 million cars because it wasn't able to fix the vulnerability over the air. Here we see a demonstrable topology with 3 ECUs, and one of those ECUs has access to some sensors, for example, acceleration sensor, and the ECU sends the values of these acceleration sensor periodically, for example, every 10 milliseconds, and for this it uses one ID, for example, 10. And potentially every ECU on the bus can receive this message, but only if it's configured to, it really will do. And here, for example, only the brakes uses acceleration data. And now we have a third ECU on the bus, which has, for example, some wireless interfaces, which can be attacked by an attacker. And now an attacker is able to use the same identifier, which is normally only used by one ECU. And the brake is not able to check if the now received message with identifier 10, for example, is really sent by the expected ECU. We look here into the controller area network, which is the most used communication bus in the in-vehicle area, and a signal is transmitted over 2 wires, CAN high and CAN low. The low CAN low is the inverse of the CAN high, and the difference between them is the actual signal. CAN provides a bandwidth of 500 kilobits and has a payload of 64 bit, and it offers, as already mentioned, no sender authenticity. Normally you would apply message authentication codes, but it's really hard to do here because we have this very limited payload size. Normal recommendation is to use at least 64 bits for a MAC-tag, and this corresponds to the payload size, so you can decide to transmit data or MAC-tag. Of course, you can also reduce the MAC-tag much more, but this still halves, for example, the bandwidth. And this also requires additional computational resources for all the ECUs, because these must calculate and verify the MACs. Another technique is are intrusion detection systems, for example, signature-based. Here the system looks for some kind of patterns, attack patterns, and if one of these patterns is present, then the system triggers an alarm. Another idea is anomaly detection. Here you specify the behavior of the car, the normal behavior, and if this is in some kind violated, then the system triggers an alarm. But these are very prone to false positives because it's not that easy to specify the exact communication behavior of a car, even if the communication is static. But there are so many different possible configurations in even one model. The third point here is physical properties, for example. You can use clock drifts or variations in the analog signal, and this is exactly what we are using in our work. Here you can see a differential rising edge of 2 different ECUs. And even with your eyes, you can see that there is a difference. For example, the red one has some kind of an overshoot at the beginning, while the black signal is much more stable and has a higher voltage level at the end of the symbol. And this is caused by the topology, by the grounding, by energy supply, and also by component variations, which come industrial typical with 5%, for example, for transistors. Here's an overview of our system. The first step is that we sample the signal. Then we slice each symbol or bit into pieces and distribute them into three possible groups. And from these groups, we extract several features, which are then fed into a classification algorithm. And now we can, based on the results of this classification algorithm, we can decide to trigger an alarm or not. The first step, as I said, is the sampling. Here we sample or record a signal with 20 megasamples per second. We use the differential signal as it contains less noise than the high and using the high and low directly. This is already a reduction in necessary sampling rate, because related work use sample rates between 2 and 2.5 gigasamples. Then we cluster the symbols based on the shape. We start after the ID, because the ID is potentially influenced by other ECUs due to simultaneous access at the beginning. We have rising edges. We have stable high signals, falling edges, and of course stable low signals. But these are discarded, the low one, because they are basically zero with some noise. Then we have these three groups: the stable high signals, the rising edges, and the falling edges. And out of these signals, we now calculate statistical features from time and frequency domain, for example, mean, standard deviation, and so on. And we calculate these individually for each group. And this is very important because I can demonstrate it here. Here you see a concatenation of 3 bits: a rising, stable signal, and a falling edge. And you can see there's a difference. But if you now calculate the mean over the whole sequence, then you get a really tiny difference. But if you calculate the mean over the rising edge, for example, over the falling edge, and over the stable high signal individually, you see a much bigger difference. And we can now use this for classification algorithm. We use simple logistic regression. This algorithm gives you probability for each ECU, how probable it is that this ECU is the sender of the received frame or of the recorded frame. We use 200 frames per ECU for learning, and it has to be ensured that the initial training is in some kind of a safe environment to avoid poisoning attacks. For example, you can do it during the manufacturing of the car or in an authorized workshop, for example. And the initial training has to be initiated by some kind of secure diagnostic access to avoid that an attacker can just retrain the system after it is modified. And we share here a key between each ECU and the system. The next step is a performance monitoring. Here we look at the probabilities of each ECU, and this because it's necessary to observe these due to aging or corrosion, if there's some change in these variations and in the templates. And the monitor monitors the probabilities of each ECU, and if the probability drops, for example, from 99 to 95%, then it updates the model, and therefore it can use the normal frames, which can still be distinguished very well. But if this drop is much harder, it's necessary to use some kind of a Mac supported learning, and this is the reason why we share a key in the previous step. For this, you can use the AutoSAR secure onboard communication module, which is available in modern cars. Yeah, and based on this classification, we can now decide if we want to trigger an attack or an alarm or not. And of course, you can just choose the highest probability. And here, for example, ECU 0 seems to be the sender of the received frame. And as we know that the communication is static in in-vehicle communication, we can say, okay, identifier 10, for example, is normally sent by ECU 0, and then everything is fine. But what is if another ECU was selected for being the sender? Then we can trigger an alarm because we know that it's normally not allowed to use this identifier. But as I already mentioned, anomaly detection is prone to false positives, and we really want to reduce false positives because it's definitely annoying for the driver also when the system says every 10 minutes, please stop immediately. And this can, for example, occur if due to some interferences, for example, if you start a strong consumer or something like that. And what we really often, or what we have observed is that if the system is not really sure, then the percentages are really look like the same. And this is why we introduced another threshold, and for example, 70%. And we now only trigger an alarm if the probability of a probable invalid ECU exceeds this threshold. This leads, of course, in turn to a higher false negative rate. So we also evaluated our approach on a prototype, which consists of 10 ECUs. We recorded 55,000 frames and achieved an accuracy of 99.9%. The bus contains of 5 Arduinos, each equipped with 2 CAN shields. Our second evaluation was done on a Fiat 500. Here we collected 26,000 frames. And we have here 6 internal ECUs in the car. And we connected 2 additional to increase the size of the ECUs and also to send forged messages. And here we achieved an average accuracy of 99.6. And the second car on which we evaluated our approach is a Porsche Panamera with also internal 6 ECUs on the powertrain bus and 2 additional to send forged messages. Here we recorded 6,000 frames and achieved an average accuracy of 99.88%. But we have an overall identification rate of 99.85%, which is an increase compared to related work. But we still have false positives, for example, after, in this case, 666 frames are transmitted. And this is the reason for our threshold, which I mentioned before. And we've also evaluated this. Here we see the false negatives reduced to 0%, so we don't see any false positives. Sorry, the false negative rate increases slightly in case of the prototype and the Porsche, and in for the Fiat, there are no false negatives and no false positives. I see I have some time left, so I skip the next page. Yeah, I see. You may ask yourself how stable this approach is. So in related work, they have also tested how long these variations are stable, and we can also make a mark at this sentence here. We've also tested this, and what we additionally have done is we tested the Fiat in some kind of different temperatures. The first measurement was done while the engine was off at an ambient temperature of about 25 degrees. And here we collected 3,000 frames, and we used the first measurement set for the training. Then we started the car, drove for 30 minutes at an ambient temperature of 32 degrees. And here we collected over 6,000 frames. And these could also classified with a 100% identification. And the third measurement was done after the car was parked 3 hours in an underground garage to cool it down. And then we drove another 20 minutes, and this also includes the start of the car. And it was really hot on this day. We had an ambient temperature of about 36 degrees. And here we've collected also over 4,000 frames and achieved an identification rate of 100%. And the biggest change which we observed was in the voltage level. So the other characteristics stay intact, which is why the identification still works. Yeah, and now the question is, what do if you detect an attack? You can warn the driver, but what is if false positives occur? So that's annoying, or yeah, it's still a question in the automotive area what to do. You can log the attack, and if you visit a workshop, someone can read the log and send it to the manufacturer, for example, to fix possible vulnerabilities. Or you can try to prevent the attack. So if you're really fast with your classification, you can, for example, invalidate the CRC, or you can send an error frame. But here it must be you must really sure what you're doing, because in safety critical buses, it's really maybe it's not a good idea to do. And another idea is to send possible attacks onto the cloud, and there you can analyze the attack, and you can maybe send some kind of a pattern you have observed onto the signature-based IDS, which is a fast fix for the vulnerability which you have detected. And then you can investigate the problem and fix the vulnerable ECU on the next update, for example, which you can also deploy over the air. Okay, then my conclusion. We have shown send identification based on physical properties of the CAN signals, and we've shown a reduction in the necessary hardware requirements due to the sampling rate. And this, of course, also requires less computational effort because we record less values. We evaluated our approach on 2 series production cars, had a high identification rate of over 99%, no false positives. And we think that our system can improve the security of modern cars, for example, as an IDS extension, or as additional security functionality for gateways which connect different buses, as a standalone system, as we have used it here. And as an outlook, we want to reduce the performance requirements much more, the hardware requirements, and we want to implement it on an embedded platform. Thank you, and if you have questions.
Okay, if you have questions, please come forward and use the mics. Perfect, and maybe also state your name and affiliation.
Okay, thanks a lot. Thanks for the great work. Actually, it was very interesting, but even though you still covered about the stability or robustness of the signature, but I still doubt that, because it was 6 months period of time with the one car. So I drove my car about 10 years. Therefore, I want to ask you for any kind of theoretical, like a guarantee that the signature will be intact over time. That is one question. And because you are from the Bosch, so I had my second question is that I always have the question about that. It is all about the standard identification, and this is communication between the ECU and car. So why can't we just come up with a better protocol with the sufficient identification? Yeah.
Thank you for your question. So why can we just use another protocol? Because everything, it's not that easy to change it. Yeah, it's the idea of many researchers or also of the industry to change it, but you have so much software and hardware which has to be updated, and this looks like a problem. Mm-hmm. And your first question, yes, of course. What is if I drive the car not just for half a year, but for 10 years, for example? This has to be, someone has to look if this also works for 10 years. But this is the reason why we have an update mechanism. Mm-hmm. But our work which we are working on in the next time is to ensure that this also works under if the signal changes.
So did you put your car in some extreme condition like very cold weather or the very hot, and that may affect the voltages?
The car, you mean?
Yeah.
That is exactly what we tried in the stability measurements. Yeah.
Okay. Thank you.
Thank you.
Hi.
Hi.
I just wanted to ask a clarification. On slide 9, you put the evaluations and evaluation table.
Sorry, the slide?
On slide 9, I think. Yeah.
This one?
Yeah, the rows at the top are different test sets, or you also trained on that? I mean, were they just different test sets in which you kind of tried to detect the attacks?
You mean the
prototype flattened Porsche rows?
On the above or the below?
The top part.
The top? Here we don't have any intrusions. If you mean this.
Oh.
The intrusions were on the table below. Here we use the two additional equipped ECUs to send forged frames for the Fiat and for the Porsche. And in the prototype, we were able to control all ECUs.
Oh, okay. And so the accuracy?
The accuracy is just identification. So just we observed the bus and checked if we identified the received frame right.
Oh, okay. Thanks.
Yeah, welcome.
Okay, we don't have too much more time, but maybe one more question here.
Thanks. So thanks for the talk. I'm Gabor Gulyás, and my question is related to the scalability of this measurement study. So for instance, if you have 10,000 of one of these cars, is it going to still work? Because maybe you have to train it for every vehicle, right? Because, for instance, one of the devices inside is going to work a bit differently than the others, so you have to train it for those signals, right? So then you have to train it for every car in the factory.
For every car, yes, that's right.
Okay, so that was okay.
And this this isn't a problem because the training is about on a PC, about 1 second.
Okay.
Yeah.
Thank you.
Thank you.